Associative property of multiplication of natural numbers is one of the fundamental properties of the set of natural numbers. We shall prove this property using the distributive law of multiplication of natural numbers over addition. The definition of addition and the definition of multiplication will be used in proving this important result. We also use the principle of mathematical induction, or the fifth axiom of Peano of natural numbers. The property says that, when we multiply three or more natural numbers, the grouping of the consecutive numbers does not affect the result. For example, when we multiply 2, 3, and 4, multiplying 2 and 3 first, and the result is being multiplied by 4, we get 24. We get the same result if we multiply 3 and 4 first, and the result is being multiplied by 2. Associative property, together with commutative property, makes it easier to do mathematics on the set of natural numbers. Proof of the associative property of multiplication. It says, a times b times c equals a times b times c for all natural numbers, a, b, and c. First, let us recall the definition of addition. Any number a plus 0 equals the number a itself. Any number a plus successor of any number, b equals the successor of the number a plus b. Multiplication of any number a by 0 is 0. Multiplication of any number a by the successor of any other number b is a times b plus a. Next, recall the distributive law. A times b plus c equal to a times b plus a times c for all natural numbers a, b, and c. Proof of the associative property of multiplication of natural numbers using distributive law of multiplication over addition. Let G be the set of natural numbers C, such that the proposition holds true for all natural numbers A and B. First base case, when C equals 0, left-hand side is a times B, times 0 equals 0, the definition of multiplication. Right-hand side is a times, B times 0 equals 0, also by the definition of multiplication. Therefore, left-hand side equals right-hand side. So, 0 is in the set G. In other words, the base case holds for the principle of mathematical induction. Next, the inductive step. Assume that C is in G. We shall show that the successor of C or S of C is also in G, or a times B times S of C equals a times B times S of C. First, let us evaluate the left-hand side. By using definition of multiplication, it is a times b times c plus a times b. In the next step, we use induction hypothesis and the expression is simplified. Secondly, let us evaluate the right-hand side. First, we evaluate the value of b times s of c. By the definition of multiplication, we have b times s of c equals b times c plus b. In the next step, we use the distributive law of multiplication over addition. Therefore, the right-hand side is equal to a times b times c plus a times b, which is exactly the same value of the left-hand side that we found earlier. So after using the definition of addition, the definition of multiplication, and the distributive law of multiplication over addition, along with the induction hypothesis, finally, we have that the left-hand side value is equal to the right-hand side value. This means whenever the proposition holds true for C, it is also true for S of C, or the successor of C. It is the most crucial part of the proof, using the principle of mathematical induction. From here onward, since the proposition holds true for C equals 0, it is true for 0 plus 1 equals 1, for 1 plus 1 equals 2, and so on. So, for all natural numbers a and b, the set of values of natural numbers c, such that the proposition holds true, is exactly equal to the set of natural number itself, or g equals n. Hence, for all natural numbers a, b, and c, the statement of the theorem holds true, or the associative property of multiplication holds true for the set of natural number. So we have just proved one of the fundamental property of the multiplication of natural numbers.